Okay, so the next video is going to be about pH, okay, pH of a solution after an acid and base reacts. Okay, so we want to know the pH of a solution. Now some of you ask me, so what do you mean by pH of the solution? Okay, let me do this one example first. Okay, see whether you understand this. Okay, let's say we have a solution here, and this solution is potassium hydroxide, and we know potassium hydroxide is a base. So let's say we have 50 ml of potassium hydroxide and the molarity is 0.15 molar. Okay. Then what we're going to do is we're going to mix it with another solution. We're going to mix it with another solution, and let's say this solution is HCl. And okay, so we're going to take an acid and then we're going to react it with a base, and let's say this is 75 ml and this is 0.12 molar. Okay, so when we mix it together, we're going to get a final solution, and this final solution is going to have a volume of, let's say, 50 plus 75. It's going to be 125 ml. Okay, I hope I got that correct. 75 plus 50, yep, 125 ml. Okay, now just want to let you know, when you see this m, right, this m is actually times 10 the power of -3. So times 10 the power of -3 liters. So this is actually 125.0 times 10 the power of -3 liters. Okay, it is the same as, you know, if you decide to take 125 divided with 1,000, you want to convert this to liter, you end up getting 0.125 liter, correct or not? So 0.125 liters is the same as 125 times 10 the power of -3 liters. It's the same thing. Okay, anyhow, let's get back to this. So we take 50 ml of sodium hydroxide and 0.15 molar, and then we're going to mix it together with 75 ml 0.12 molar hydrochloric acid. Okay, so we're going to mix this together. So what we're going to do is we want to find out what is the pH of this resulting solution. What is the pH of this? Okay, what's the pH of this? You see, usually our understanding is when an acid reacts with a base, it's going to be completely neutralized, which is not true. If you have more acid than the base, the end solution is going to be acidic. If you have more base than acid, the end solution is going to be basic. Okay, so let's solve this problem. Step number one always is to find the moles. So we want to find the moles of, let's say we want to find the moles of potassium hydroxide. Okay, so what we're going to do is we're going to take 0.15 molar times 50 divided with 1,000. So this will give us the mole of potassium hydroxide. So 0.15 times 50 divided with 1,000, it is 7.5 times 10 the power of -3 moles. Okay, and then now I hope you know that this is actually a mono basic base. So the mole of hydroxide is the same as the mole of potassium hydroxide, which is 7.5 times 10 the power of -3 mole. So we have 7.5 times 10 the power of -3 moles of hydroxide ions. Okay, so we're interested in that. Let's do for the acid. So for the acid, we have number of moles of HCl is 75 times 0.12 divided with 1,000. And let's do this. 75 times 0.12 divided with 1,000, you get 9.0 times 10 the power of -3 mole HCl. And what I want you to notice is HCl is a monoprotic acid, monoprotic. So which means that, what does it mean? It means that the number of moles of hydrogen ions that you can get from HCl is exactly the same as the number of moles of HCl that you have, which is in this case this much. Okay, so we have that many moles of hydrogen and we have that many moles of hydroxide. Now, if you remember earlier today, in the earlier video, just the video before this, I told you about this equation here, this one, this equation, okay, or which one? This equation here, this one, this equation here, all right? Okay, so we're going to use this equation, hydrogen and hydroxide. Okay, so let's go back to this. All right, so what I want you to know is one hydrogen combines with one hydroxide and it will give you water. Okay, it will give you water. So in this example, if you watch carefully, we have 9.0 times 10 to the power of negative 3 and we have 7.5 times 10 to the power of negative 3. Okay, can you see that? Now, what I want you to know is, can you see that the ratio is supposed to be 1:1, correct? So if this is 9.0 times 10 to the power of negative 3, this should be 9.0 times 10 to the power of negative 3. Yes or no? It should be. But it's not. It is only 7.5. So if this was 7.5 times 10 to the power of negative 3, this should also be 7.5 times 10 to the power of negative 3 for a complete reaction. Complete reaction, that means completely neutral. So I hope you can see currently there appears to be more hydrogen than hydroxide. I hope you can see that. Okay, more hydrogen. So how much more is that? So very simple, because the ratio is 1:1, we just minus lah. So when we minus 9 minus 7.5, you get 1.5 times 10 to the power of negative 3. What am I doing? Negative 3 mole of hydrogen. That's the amount of hydrogen which is excess. Do you understand? If you don't, pause this video and try to reflect. So we have more hydrogen. So when the reaction is over, in this solution here, you're going to have hydrogen ions running around. Hydroxide, there is none anymore. There are going to be hydrogen ions. So we have this many hydrogen ions and the final solution is 0.125 molar. 0.125 liters. Can you see this? So very easy. We are going to calculate the molarity of the hydrogen ions, which is going to be 1.5 times 10 to the power of negative 3 divided with, what was the liters just now? 0.125. Okay, 0.125 liters. So this is mole. So I hope you remember molarity is mole over liter. So 1.5 exponential negative 3 divided with 0.125, I'm getting a concentration of 0.0125 molar hydrogen ions. So pH will be negative log 10, 0.0125. And this would be, let's log this, 1.921. But let me just check all my calculations again. If I see this is two significant numbers, so I'm going to bring my pH to two significant numbers. That will be my safest bet. So 1.9. Okay, so that is how I calculate the pH of my solution after an acid and a base reacts together. Okay, so let's try another example. Okay, let's try another example. See whether we understand the concept. So these type of questions are only useful for strong acids, strong bases. Weak acids, strong bases we can't really use it. okay, or weak acid is even, weak acid and weak base is even worse. It's even worse. Okay, so let's say we have two solutions, all right? So we have solution one. Solution one is barium hydroxide, and then we have 50 ml of this one, and the molarity is 0.10 molar, okay? And then let's say we have solution two. Solution two is, let's say, nitric acid, and this is, let's say, 80 ml, and let's say this is 0.12 molar, okay? So the question now is, if I mix solution one and solution two, what would be the pH of the resulting solution? What is the pH of the resulting solution when I mix them together? Okay, so just like just now, let's work out first things first. Number of moles of barium hydroxide. Okay, number of moles of barium hydroxide will be 50 times 0.10 divided with 1000. Okay, this would be 50 times 0.1 divided with 1000. So I get 5.0 times 10 the power of negative 3 moles. Okay, but then I want you to notice that this is what? Dibasic. So the number of moles of hydroxide is 2 times the number of moles of barium hydroxide. Yes or no? So in this case, it's going to be 2 times 5.0 times 10 the power of negative 3 moles. So which will be 10.0 times 10 the power of negative 3 moles hydroxide. That is the amount of hydroxide that we have. So how much of acid do we have? So number of moles, let's say number of moles of nitric acid. Now nitric acid is monoprotic, right? Or it's only one. So this would be 80 times 0.12 divided with 1000. So what do we get? 80 times 0.12 divided with 1000. So we get 9.6 times 10 the power of negative 3. And since this is monoprotic, the number of hydrogen ions that I can get should be exactly the same as the number of moles of the acid, which will be 9.6 times 10 the power of negative 3 moles. Okay, so I know the number of moles of hydroxide and I know the number of moles of hydrogen, and then I'm going to go back to my original equation just now. Hydrogen plus hydroxide gives me water. This is liquid, this is aqueous, right? So the ratio is 1 to 1 to 1 to 1, right? Hydrogen is 1, hydroxide is 1. So how much of hydroxide do I have? I have 10 times 10 the power of negative 3, and this one is 9.6 times 10 the power of negative 3. Okay, so I hope you can see here, there seems to be more hydroxide compared to hydrogen. Yes or no? There seems to be more hydroxide compared to hydrogen. There seems to be, how much more? Okay, because the ratio is supposed to be 1 to 1. So now it's 9.6 versus 10. Okay, so hydroxide is more than hydrogen, right? So by how much? So it's going to be 10.0 exponential negative 3 minus 9.6 exponential negative 3. Is excess by 4.0 times 10 the power of negative 4 moles. All right, so we take this number and then we minus off this number, the bigger number minus smaller number. So this is number of moles of hydroxide excess. So when the reaction is over, there is still this much of hydroxide running around. So what is the total volume now? What is the total volume? Let's go back here again. It was 50 ml and 80 ml. 50 ml and 80 ml. 50 plus 80 ml. So this gives me 130 ml. I'm going to convert this to liter. I'm going to divide this with 1000 and I get 0.130 liter. Okay, so now I'm going to find the concentration of hydroxide. So which is going to be 4.0 times 10 to the power of negative 4 divided with 0.130, which is the volume, right? Divided with 0.130. Wow, I get such a small number. It's 3.077 times 10 to the power of negative 3 molar. That's the molarity of the hydroxide. So I use POH will be negative log 10, 3.077 times 10 to the power of negative 3 molar. Okay, so let me log this. Log, I get 2.5, let's say 2.51. Okay, let's say 2.51, right? Let me go back and look at my calculations again. This is two significant number. So basically, I should have two significant numbers in most of my places. All right, so this should kind of end up with 2.5. Okay, but I'm not done. Sorry, I'm not done yet. Actually, I'm not done yet. So pH will be 14 minus 2.5, right? So this is supposed to be 14.0 lah. 14.0. But this 14.0, if you take 14.0 plus 14, you get 11.5. So 11.5, because you see it's 14.0 minus 2.5, right? Okay, so it's going to be what? 13. 1 goes here. 5. 13 minus 2 is 11, right? So we are supposed to leave our answer now, because we are not multiplying, we are minusing. It is decimal places, so it's 11.5. But let's say some of you decide, hey, I don't want to use 14.0, I'm going to use 14 minus 2.5. Okay, if you decide to do that, no problem. We do the exact same thing. You still get 11.5, but we're going to round this up to 12. So for those of you who decide to use 14, your answer will end up as 12. It's okay. It depends on what you want to use. Okay, whether you want to use 14.0 or 14. If you use 14, it's going to be 12. If you use 14.0, it's going to be 11.5. It's acceptable. All right. So that's basically how we do this calculation. Now, the only thing I want to tell you is, please pay attention to what I'm going to tell you. Let's say when you calculate the number of, let's say in a question, you calculate the number of moles of hydrogen and hydroxide. Let's say when you do the calculation, right? When you do the calculation, let's say in this question, let's say if this was actually 10.0 times 10 to the power of negative 3 as well. Let's say if you end up with the number of moles of hydrogen and hydroxide to be exactly the same, okay, exactly the same, then what happens is there is total annihilation, completely neutralized. So the pH automatically becomes 7. Please remember that. When you do this calculation, and if you calculate the number of moles of hydrogen and the number of moles of hydroxide to be exactly the same, okay, let's say one is 0.02 and the other one is also 0.02, then rest assured the pH is going to be 7. So you just have to say OH same as H, pH is 7. That's it. You don't have to continue doing all of these calculations. Don't have to. Automatically understood pH is 7. Okay, so please remember that. Okay, I hope this helps you with your calculations. Thank you.